Welcome everyone to this problem solving session for Physics 112. In this session I'll talk about problems regarding electrostatics. Before this I've taken a problem solving class, and we started from chapter 24 from our beloved textbook Halliday, Resnick, Walker. So that's the textbook we are following. Specifically, I'm following the 10th edition, and that's where I have suggested you the problems from 10th edition. And I suggest you solve those and solve this as early as possible, and then start from this video. So I'll try to cover as much content as possible in this video. It's entirely about problem solving tricks and problems themselves that I've suggested, that were suggested in the course outline. So I'm gonna tackle them one by one, just like we did before, and I intend to upload this video on YouTube. So in the description you'll find a link to the previous resources and the previous videos as well. And I'm doing this only for you, so that you can invest as much time as you want in your own style, in your own fashion, and prepare yourself better for the upcoming exam. So I warn you once again, just like before, I'm not going to solve everything down to the number. Right, the numbers are your responsibility only, so I'm not gonna use a calculator to plug in the numbers and then find out the exact result. You are the one who will be responsible for that. But I'm going to give you the not only the clue, I'm going to effectively solve the problem for you, and the number part is your responsibility. And you are already familiar with all of this, how it went the last time. I hope it was useful for you. I'm also going to provide this open book content in the form of a PDF, just as I did before. So in the description of this video you should be able to find a drive link, Google Drive link, where I will upload the PDF regarding to this open board file. And I'll upload the previous one as well, so don't worry about it. Okay, so this is the book, and we're in chapter 24 in the exercise, or in the section of unsolved problems, and 23 number right here. So I should be able to draw here with the pencil option. Okay, so this 23 number right here was one of the suggested problems. So let's try to solve it. What does it say? It talks about a non-conducting rod of length L equal to 6 cm. So the details of L is not important for us, or at least for me now. It will be important for you in the exam hall, of course. At a uniform charge density, so charge density is again constant, just like all the problems we've done every time we had to deal with continuous charge distribution. The density was always constant in our problems. Assume that electric potential is defined to be V equal to 0 to infinity, which is what we always assume, right? The potential is 0 when you go infinitely far away. What is V at point P at a distance D equal to 8 cm along the rod's perpendicular bisector? Okay, so where are we? We are here, right? So this is 8 cm. The question is, what is the potential? So I think what you can assume is the fact that as soon as we're going to deal with a continuous charge distribution and the potential is a single point at a certain distance away from the distribution, you immediately understand that we have to take refuge to integration, right? We have to do some sort of integration in order to get an answer. Okay, so that's the first problem. It talks about the fields along the perpendicular bisector of a charged rod of finite length. Okay, what's the second problem? What's problem B? Okay, so this is the figure for problem B. It talks about an identical rod, but notice here we have plus charges, whereas on the right side we have negative charges, right? So the density remains the same, everything remains the same, but the charges have changed their nature. Instead of being plus on both sides, one side is still plus, but the other side has now switched on to the negative polarity, negative charge distribution. So both halves have a linear charge density of magnitude this with v equal to 0 at infinity. What is v at p? So this is from the chapter 24, problem number 23, right? So problem 23. Okay, so we have a distribution. So how can I draw a line of charge? So this is a line of charge. I should be careful about drawing a perpendicular bisector. So this is the charge distribution, right? And this line is in the middle. So let me choose a thin line, and this is in the middle. So as the problem suggests, this is D. Oh, that doesn't look good. Okay, this is D, yeah, and this is L by 2, L by 2. All right. And there's a charge distribution on it, the charge density, lambda. So I should assume the total charge Q should be equal to lambda times L, right? Since lambda is a constant, it doesn't depend on the position. Okay, what can we do? Let's choose this distance right here, which should be small l, and this length would then be square root of d squared plus l squared. So that's this distance. At a distance L, we choose a small segment, line segment, which is dl. Okay, so the charge in the dl would be dq, which would be equal to lambda times dl. Okay, so as you can notice, if we integrate over this, lambda is a constant, comes out of the integration over dl gives us L. So we can go from here to here very easily. So that's a good checkpoint for us. Okay, what else? We need to find out the potential. Now, potential, as you know, is V. So according to the formula for the point charge is going to be 1 by 4 pi epsilon naught, 4 pi epsilon naught. And then we had R being the distance, and of course in the upstairs we had the charge Q. So in this case, however, we go toward the modification for constant charge distribution. So this is for point charge. I should outline it, or you'd probably get confused. This is for point charge, right? Or discrete charge distribution. If you had multiple charges, then all you'll need to do is you have to sum up over all the charges, right? So I indicates which charge you're going to talk about. So if I is equal to 1, then it's about charge 1, which is at R1 distance away. If I is equal to 2, then you're talking about charge Q2, which is at R2 distance away. Do you understand what we're doing? And then you, of course, have to sum up all such terms for all such source charges. Okay, so what we are going to do here is this gives us a differential contribution to the potential by the charge dq. Okay, so divided by 4 pi epsilon naught r, and of course 4 pi epsilon naught, which is the Coulomb constant, well, 1 over 4 pi epsilon naught, which is the Coulomb's constant, gets out of the integration. So when you integrate this, you get the total potential, which is the quantity we're looking for, and this would be 1 by 4 pi epsilon naught, an integral over dq over r. right? Now, I know you're thinking this is difficult. This probably seems to be difficult at the beginning, but trust me, this is easier than what you think. So, for our case, dq is equal to lambda times dl. And what is the limit of L? So L goes, so the lower limit of L, right? The lower limit, L low, is going to be minus L by 2. So what we're doing here, so we are establishing a coordinate system. So we are deciding that this line is going to indicate the y direction, and this line here is going to indicate the x direction. So this would be plus L by 2, x equal to plus L by 2, and this is of course the minus L x direction. So this line, this point would indicate x equal to minus L by 2. All right, just for simplicity, and of course the middle point is going to be the 0. So its lower limit is the I should change the color. Its lower limit is negative L by 2, and its upper limit, is going to be plus L by 2. So these are for integration. So let's set up the integration. So v is equal to 1 by 4 pi epsilon naught, and create the integration. So remember what dq was. Dq was lambda dl. So lambda comes out. So that's the lambda, right? And then I have dl over. Instead of this distance, I have just found out this distance is a square root of d squared plus l squared. Minus L by 2, and then you have L by 2. Okay, so as we have done before, if we take L equal to d, then tan theta, right? If we make this substitution, then of course dl is going to be equal to d sec squared theta d theta. So you just plug them in. So in the denominator, right, what do we find? We find square root of d squared plus l squared equal to, right? Okay, I should be careful about writing. So this would be square root of d squared plus d squared tan squared theta. You take d squared out, so it's inside the square root. So if you take d squared out of the square root, you just simply get d. So inside you have 1 plus d, 1 plus tan squared theta. Terribly sorry for this. Tan squared theta. And then this is going to give you d. So 1 plus tan squared theta is sec squared theta. You have the square root, so it's your sec theta. Okay, great. So what do we have? We have lambda divided by 4 pi epsilon naught. The lower limit is probably going to be some theta, I don't know. So some theta 1, this is going to be theta 2. As you will see, at the end, we'll reverse back. So instead of theta, we'll go back to L. But for now, just play along. So we have d L, so we have d sec squared theta d theta. On the bottom we have, what do we have? We have d sec theta. So one of these things is going to cancel one of this factor on the top. By the way, this might be confusing. This d has nothing to do with this d theta, right? So d cancels d. So what are we left with? We're left with lambda divided by 4 pi epsilon naught. And then we have theta 1 to theta 2. And then we have sec theta d theta. Okay, so now I hope you do remember how to integrate sec theta. If you don't, then that's a shame. But I'm going to remind you here. So this is the way you integrate sec theta. Oh, if you don't remember it, I'm just going to give you the results. So sec theta d theta is going to be equal to logarithm. So log and then we have absolute value of sec theta plus tan theta. What you essentially do is you multiply this sec theta with sec theta plus tan theta, and therefore you divide it also with sec theta plus tan theta, and then it's just a simple logarithm. If you have forgotten this, go back to like your college textbooks and then find it out, or simply do a Google search. Just learn it, right? It's a simple trick. Doesn't take much to remember. So we have this, of course, right? We do have sec theta, but we want to switch back. So because otherwise we'll have to find out what theta 1 is, theta 2 is, as a headache. How do we switch back? Well, remember the relationship we started with, L equal to d tan theta. So we have L divided by d equal to tan theta, right? And therefore we have square it, I get L squared divided by d squared equal to tan squared theta. But we know sec squared theta is 1 plus tan squared theta. So if I add 1 to the right hand side, I have to add 1 to the left hand side. And that gives us the sec squared theta. So therefore, I get sec theta, right, equal to square root of d squared plus L squared divided by d squared. So that's what we get, and that's what I should write. So logarithm, and then instead of tan theta here, I'm going to write L divided by d. Instead of sec theta here, I'm going to write plus square root of d squared plus L squared divided by d squared. And then of course in the lower limit you have to plug in negative L divided by 2 at the top plus L divided by 2. So all of this I have done here is simply rough calculation, and lambda divided by 4 pi epsilon naught, you have log, then you plug in the upper limit, so I have L divided by 2d plus then d squared plus L squared, capital L squared divided by 4 divided by d squared. I know it's getting too complicated for you, but the calculation is conceptually not very complicated. Then you plug in the same limits, so I have minus, right, L divided by 2d, and then plus inside the square root. Well, when you square L by 2 and minus L by 2, you get the same result. So this portion doesn't change, right? d squared. But then of course you can always bring those together. Lambda divided by 4 pi epsilon naught. But then you have the logarithm to bring them together. Okay, so what do we find? We find log. In the upstairs you have L by 2d, and if you break it down, the latter term, you get, what do you get? Oh, that's very interesting. You get on the top, I'm just going to multiply the top and the bottom by 4 here. So in the bottom, inside the square root, you have 4d squared, which is simply 2d. At the top, you have 4d squared plus L squared. On the bottom, you have minus L divided by 2d plus square root of 4d squared plus L squared divided by 2d. Alright? Of course, everything within the absolute value. And then you have lambda divided by 4 pi epsilon naught. And then you have logarithm. Then inside you have 4d squared plus L squared plus L divided by 4d squared plus L squared minus L. And that's it. That's the potential along the perpendicular bisector. Okay, and this is of course a function of d. Seems complicated expression, but the procedure is very simple. You have to know simply basic math. And if you're weak at that, trust me, you want to rethink your choices. Either you relearn these things and pay your attention to the topic of integration, differentiation, etc. Or probably you need to rethink what you're doing right now. I don't want you to lose your precious, valuable time of your life. Anyway, let's move on to the second part of the question. What if the one of the halves of the rod is being replaced by negative charge distribution? So in order to talk about this, let me go back to the question itself, so inside the book, where I can simply point finger at the drawing itself, at the figure itself. So notice, if you're clever, then this is really interesting problem for you, because the distance from here to here, if this is L distance away, is the same as distance from here to here, which is again L distance to the right. However, but the contribution due to this charge, this positive charge, this lambda dl, is going to be negated by the contribution from this negative lambda dl charge. Why? Because you have to add up all the charges, you have to integrate. Once you recognize this, you'll notice the contribution from the left side to the point, to the potential at point P, is going to be negated by the contribution from the right side, from the negative charges, to the potential at point P. So what is V at P? Is going to be 0. So this is the plus charges, and this is the negative charges. And in the middle, because the distance is the same, right? So you can always find a counterpart of this charge here. You can always find a counterpart on the right side, from the negative side, which exactly cancels the contribution from the positive side, right? Because the distance is the same and the charge is the same, but with the opposite direction, and the potential depends on the distance and the charge. It can be well understood by another problem. So for example, this is probably in your book somewhere, but I'm just going to mention it right out of my head. So if there is a positive charge and a negative charge, and they are on a line, right? And this is the perpendicular bisector. So you choose any point, right? What is the potential on this perpendicular bisector? Well, you say if this is a dipole, so this is the distance, let's say L. So this is L by 2, and this is L by 2. And this is, let's say, D. So you notice this distance is D squared plus L squared by 4 with a square root. And so is this one, square root of D squared plus L squared by 4. So that's the distance, right? That's r, which is here r as well. So if you talk about the potential V, you talk about, well, 1 by blah blah blah, 4 pi epsilon naught. But then you take Q, which is plus Q, divided by R, and then you take plus Q2, which is minus Q, divided by R, which is 0. And the same thing is happening on the right side as well. Because of the symmetry, the potential on this line is going to be 0. It's as simple as that. Okay? So just by looking at the problem, you should be able to figure it like that the potential is going to be 0. Right? It's probably going to take you 10 seconds, 30 seconds, a minute, but that's that. Once you understand the symmetry, you'll understand the solution to the problem. That is to say, the field, the electric field, is definitely not 0. We have talked about it at length when we talked about the dipoles in chapter 22, right? Yeah, chapter 22. So the electric field is not 0, but the potential is 0. Okay. Now, let me ask you a question. How come the field be non-zero if the potential is 0? Because after all, electric field, is the negative derivative, right? So in this case, negative gradient of the potential, right? It's a negative derivative of the potential. In one-dimensional case, in one-dimensional case, E is going to be negative dv dx, or dv dy, depending on along which line you're trying to take derivative along. So how, if this is true, and then the potential is 0 on this line, you can, if you differentiate 0, you get a 0. So how come the electric field be non-zero? Interesting, isn't it? So think about it, explain it to me. I think it's a straightforward explanation, but try to explain it to me, and if you can think of the solution right away, that means probably you are understanding, you are building up your intuition on electrostatic. It's really important. It's really basic stuff. So if you allow any lackings to persist, then it's going to harm you in future. So be very careful, right? Do invest a little bit amount of time behind thinking and solving the problems, and it is going to reward you greatly. Let's move on to the next problem. Problem number 24. A plastic rod having a uniformly distributed charge Q, so the charge is being uniformly distributed around this line, has been bent into a circular arc of radius r. R has been given, Q has been given. If Q and R both has been given, then of course lambda has been given, remember. And the angle phi, this is 120 degree. So again, with V equals infinity, what is the electric potential at P, the center of the curvature of the rod? Let's find it out. Alright, so as we have discussed before, Q, phi, and R has been given. So now lambda is equal to Q divided by length. So what is the length? Well, we know if it were a circle, then it would be twice pi r, that would be L, but it's not. It only encompasses 120 degrees, which is phi. So, you know, twice pi L divided by the angle, which is twice pi. This ratio would be the same for any circumference, any partial arc, and the angle it encloses at the center. So that would be, I'm sorry, it should be R here, right? It should be radius r, and then in the right hand side we should have L divided by phi. Right, this is how we find out the relationship between the length of an arc and the angle it encloses at the center. So twice pi cancels twice pi, we have L equal to r phi. So this is going to be Q divided by r phi. So that's the lambda. And this lambda is constant because Q is constant, R is constant, and phi is constant. So, and the distribution has been performed uniformly. That's the most important thing. If it's not a uniform distribution, then we cannot say the density is constant. While this is true, we're going to find out the potential at the center. Let's call it P. So what is the potential? So choose any segment here, and that encloses an angle d phi. Okay. Now I'm going to start counting phi from here. So this is the line where phi is equal to 0, and this is the line where phi is equal to 120 degree. All right, 20 degrees. Should I call it phi something else other than phi? I think I should write phi prime here, right? And 120 degree would be the phi. Just a convenience in naming. It's nothing serious. You don't have to follow this, but it's good to follow this. It's good to differentiate the variable and the limits. So so this portion right here, right, this dl right here, enclosed by this angle d phi, it encloses a charge dq. So dq in that small segment, I should use some other color, in this red segment, the charge in this red segment is going to be lambda times dl, which is equal to lambda is q divided by r phi times dl. Yeah, yes, so I'm going to use small l here, small l. I'm sorry, but this would be the right choice. Then the potential dV is equal to 1 by 4 pi epsilon naught, then dq over r, right? Because that's r distance away from P. So the distance from this red patch to point P is simply r, okay, because r is the radius. So therefore, when we integrate for V, we have to integrate 4 pi epsilon naught r, because remember r is the radius, so therefore it's a constant. So you simply integrate over dq. And what is dq? dq is capital Q divided by r phi dl. But what is dl? dl is, so if L is this, then dl is r d phi. Right? I should write prime. So dl is r d phi prime. And phi prime starts from 0 and ends at 120 degrees, which is phi. So what do we end up with? R cancels r, phi comes out, right? So V equal to Q divided by 4 pi epsilon naught r phi, phi is on the downstairs, and then integrate d phi prime from 0 to 120 degrees, which is phi. So this thing here is going to give us phi, right? Because if you integrate over d phi prime, you get phi prime, The lower limit is 0, the upper limit is phi, so the answer is phi anyway, and that cancels this. So this is going to be simply q divided by 4 pi epsilon naught r. Simple, isn't it? So the next problem is this, number 26. It talks about a thin rod with uniform charge density. So there is a lambda. Lambda is given, right? Lambda is given. L is given. Is L given? I don't see any L. Just the value of lambda is given. Evaluate. Okay, D equal to capital D. So this thing is the same as that thing. And it is total L, okay, divided by 4. So this thing here is L divided by 4. And the whole thing is L. So just the length of the rod should be L minus L divided by 4. Okay, let's see. So this distance is D. This is D. And this here is L. Now what it says is that this D is equal to, I think I should choose in a thicker line, anyway, is L divided by 4. So if that is the case, then what is the length of this thing? So it should be L minus L divided by 4, which is thrice L divided by 4. So this is going to be thrice L divided by 4. Alright, so we start from 3. We start from D, right? That's D and that's L. So this is D. And from here I see this is 3D. That's 3D. Right? I think I've got it right. Yeah. So this figure is the same as the figure we've drawn. The only additional component that's been given is that the lambda is constant and is given to be 2 microcoulomb per meter. The question is, what's the potential at point P? So here is point P. And then, of course, the distance from, so if this is x, right, this is x, then after x, a small segment, this is dx, should have the charge dq, which is lambda times dx. So we should have dv equal to 1 by 4 pi epsilon naught, and then dq over r, and r is this distance here, which is square root of d squared plus x squared. So we have square root of d squared plus x squared. And this is simply lambda divided by 4 pi epsilon naught, and then integral of dx divided by square root of d squared plus x squared. So by now probably you have become some sort of aficionado in evaluating integral like this. It's the same procedure as before. X is equal to d tan theta, and then of course dx equals d sec squared theta d theta, and then the lower limit of x is d, right, or rather L by 4, I should say. I can also say that, can't I? Yeah, I can. I can say L by 4 and x upper limit is going to be equal to 4d, or simply L. So that's that. If we take, by the way, this d again and that d, they're not related. So this is unfortunately the problem with mathematics. We run out of symbols pretty quickly. So we have to be patient with this. So v, oh, I told I have integrated. All right, no problem. Because I have given an integration sign here, I should give it all round. So v is equal to lambda divided by 4 pi epsilon naught. And you know the drill. It's sec squared theta d theta divided by d sec theta. Integral d cancels d, sec theta cancel one of that. So we have lambda divided by 4 pi epsilon naught log of sec theta plus tan theta, right? And then of course you have to take lower limit and upper limit. So once again I have lambda divided by 4 pi epsilon naught, and logarithm inside we have sec theta, which is well, first tan theta, so x divided by d, and then sec theta would be square root of d squared plus x squared divided by d squared. I should simply say d, right? I can do that. So in the downstairs it's just d. So let me make this a little bit nicer. So we have d in the downstairs all the time. So I'm just going to write it once. So d in the upstairs I have x plus square root of d squared plus x squared. And then the lower limit would be L by 4, the upper limit would be L, right? What is that going to be? Well, hard to say, but I think we can attempt it. So I should say divided by 4 pi epsilon naught logarithm. So in the upstairs I should have L plus square root of d squared plus L squared. At the downstairs I should have L by 4 plus square root of d squared plus L squared by 16. That's the answer. Or at least that should be the answer, unless I've made a silly mistake. Okay, move on to the next one. But before I do that, I should say, if you do this once, you can do this every other time you have been required to do. So it's actually very easy. Once you get a hold of it, it's very straightforward.